chapter. Look at the formation of ions. The formation of ions we can see from the orbital in the shell. Form cations and anions. We talked about those before, but let's just take a look at nitrogen. So, for example, nitrogen can gain 3 electrons, we go to -3, or we lose 5 electrons, we go to +5. And so the range of the charge is +5 to -3. In this case, gaining 3 to complete its valence shell is the easiest. If it gains 3, it'd be 1s2, 2s2, 2p3. Gaining 3 goes to 2p6 to complete that shell. This is what we call isoelectronic with neon. It has 10 electrons. So oxygen needs 3 electrons. Nitrogen needs 3 electrons. Oxygen here only needs 2 electrons to complete that shell. Just 2 electrons short of the shell to be completed. These are the Lewis symbols we show. So when we complete that shell, we're going to have a total of 8 electrons in the second shell. So we see 8 electrons of the octet electrons here. Okay, fluorine only needs 1. Neon doesn't need any. Neon's stable as is. So the shell is completely filled. The valence shell and the core shell here. That's 10 electrons. And so 10 electrons having that filled shell is what we see for those ions. Okay, for other ions, this is just a review. For other ions, it's easier to lose. So sodium, it's much easier to lose 1. To fill the third shell, how many additional electrons would it have to gain? It'd have to gain 7 electrons. That's highly unlikely to gain 7 electrons here. And so for sodium, we lose 1 electron. And the valence shell would be the highest n, which would be 3. So we lose that 3s1. We're left with this 10 electrons filled shell. This is a Lewis symbol. Lewis symbol here, we should put square brackets over. This looks like a formula, so we put square brackets over any Lewis symbol that has a charge associated with it. This one, it's hard to write the correct. If I were to write the Lewis symbol for sodium, we'd write this. The formula we write like that. The Lewis symbol for chloride. Chloride would gain 1 electron filling its octet. Chloride normally has the 3s2, 3p5, so it's 1 electron short of chloride. It gains 1 electron, it has an octet. The formula would be Cl minus. So this is a Lewis symbol. This is the formula. Formulas. Neon, however, would not have square brackets over that because neon is neutral. When we have neutral, we don't put any bracket around that. So all these Lewis symbols are missing the brackets here. That way we don't get mixed up. And so magnesium has 2, they can lose 2. Aluminum has 3, it can lose 3. 3 has 2, 3 has 1. Your carbon, carbon's at the midway point. You can lose 4, gain 4. So we have this table here. These are fixed charges. These are always +1. These are always +2. Aluminum's always +3. Boron should be +3 too. Scandium, yttrium, lanthanum are always +3. It's easy enough to lose those 3 here. Except it's kind of weird because scandium, what are the 3 that we're losing? Did we do this one yesterday?
Yes.
Yeah. It's losing the S, of course, but it's also losing a D electron, as all of these are. Okay, once we have that, then these are all variable charge. Except here, we have the 2B and the 1B group. 2B and 1B group, which are fixed charge. fixed. And so why do we want to form these ions? Why we want to form these ions is to form ionic bonds. And so when we do this gives us a sense. The quantum mechanics is the basis for forming these charges. It's also the basis for forming the bonds because we're looking at electrical interactions here. So if I take sodium like this with one valence electron and chlorine like this, now I'm going to do, this is going to be atomic chlorine. I'll talk about molecular chlorine shortly. But if I take atomic chlorine like this, well, chlorine wants to gain one electron and sodium can lose one. And so what we end up with is forming the ionic compound sodium chloride. This. And what holds together these two ions is electrical attraction. There's going to be an electrical attraction. And essentially these are like charged balls. You have a sodium, which is a positive ball, and a chloride, which is a negative ball. So you have a positive and negative ball, they're going to attract each other. They're going to be held together. This electrical attraction is called an ionic bond. If you have a positive ball, then all the negative balls are going to be attracted to it. And so when we look at it, what is going to happen is this would be a formula unit. But what will eventually happen is you're going to have a positive ball, and the positive ball is going to be surrounded by as many negative balls as possible. It turns out you can fit 4 negative balls in the same plane, and then you can stick 1 negative ball on the top. And there's going to be 1 negative ball here, and then 1 negative ball underneath. And so altogether, there are going to be 6 ionic bonds. Each sodium ion has 6 ionic bonds. 6 nearest neighbor ionic bonds. And then each chloride, if we look at each chloride is going to have 6 as well, because there's going to be 4 sodiums in the plane. These are just positive and negative, so you try to mix the positive and negative so that there's as much favorable interaction as possible. So we build up, this is the sodium chloride lattice. So sodium chloride ionic lattice. Ionic lattice is you have these charged balls and you just try to pack them together to maximize the number of negative balls in contact with the positive balls and the number of positive balls in contact with the negative balls. You get that lattice. All right, so let's try this active exercise here. Write the electron configuration for calcium ion. But before we do that, we probably should just write the electron configuration for calcium first. Let's try that. Calcium has how many electrons? Yeah. Let's look at the periodic table here. It's 20 electrons. 20 electrons. So it's going to be 1s2, right? And then what? 1s2, what comes after 1s2? 2s2, 2p6, 3s2, 3p6. Well, how many does that make? We got 10, 18, 4s2. All right. What we have here is the core, and then we have the valence. The valence is going to have the highest N. And how many valence electrons? So what we do is we sum up. We don't care about what subshell, we just look for the highest N. In this case, there are two valence electrons. 2 valence electrons. And the rest are core, so we're going to have 18 core electrons. 18 core electrons, 2 valence. Now, calcium is going to be oxidized and form calcium what? Well, it doesn't have to be oxidized by oxygen. It could be oxidized by any other oxidizer. In fact, a lot of oxidizers can oxidize calcium. As we think about what oxidizers can oxidize calcium, let's just take a quick peek at that. You know, calcium metal will react with what oxidizers? So let me get this up. So, oh, I thought my tabs had. Lots of things can oxidize. Calcium is a very reactive metal. In fact, all these metals here are highly reactive. It doesn't take a very strong oxidizer to oxidize any of these metals. In fact, a terribly weak oxidizer. What's a terribly weak oxidizer? Can you think? Is water a powerful oxidizer? You know, when you drink water, so you drink antioxidants to counter the oxidation power of water. No, water is a terribly weak oxidizer, but water is plenty powerful enough to oxidize calcium. No problem about that. What else can oxidize? Can you believe sodium ions can oxidize calcium?
Wow.
That's pretty impressive. I mean, because sodium ions, are they very reactive? No, I mean, you can sprinkle those on French fries. You don't worry about oxidizing your fries. You don't worry about oxidizing your body, right? Well, actually, you aren't going to find these metals here. These guys are very reactive. And so sodium ions can oxidize, magnesium ions. It doesn't have to be oxygen. Oxygen is a pretty powerful oxidizer. We could use something much worse to oxidize it. And so we don't know what the oxidizer is. Just some oxidizer is going to come in and pull the electron. Calcium is a really good oxidizer because it has a low ionization energy or a high ionization energy. Calcium is a really good oxidizer because it has a low ionization or a high ionization. Or calcium is a good, not oxidizer, calcium is easy to oxidize, let's say. Calcium is easy to oxidize because it has a high ionization energy or low ionization energy? Low, good. Low. And it's going to be oxidized to what? Well, what's the electron configuration for calcium 2 plus? Just do the whole thing. It's going to be 1s2, 2s2, 2p6, 3s2, 3p6. Redox chart. Then let's go back to this.
For the first electron configuration, why did you skip 3D?
Why did I skip 3D?
I thought it was
It's because 3D is promoted up to the next shell, actually. 3D, you know, you would think it'd go 3S, 3P, 3D, but it doesn't. The ordering's all mixed up. The ordering's all mixed up. It has to do with reasons, which I skipped entirely, but is covered in Chem 1A. The reason is it has to do with something called shielding and a penetration of orbitals. And so it depends on the shape of the probability distribution, and the 3D happens to get bumped up in order. And so, you know, it's something you just have to memorize for right now. You have to memorize it, and the easiest way to memorize it is by drawing this chart like this, etc. And so the way we figure out what the order of filling, this is the filling order for the orbitals. This is not the removal order. You know, the removal order is different. The removal order would be like what you're thinking. You would think in terms of progression, numerical progression and alphabetical progression. And so these are things you just have to memorize. The filling order is weird, it's like this. The removing order is numerical. The filling order is different than the removing order. That is, an oxidizer comes along, it doesn't oxidize, the reverse of the filling. And so it goes 1s, 2s. You do these down arrows like this. 2p, 3s, 3p. It doesn't jump from 3p to 3d, it jumps from 3p to 4s. And then you memorize that. When we remove it, the removing order is like this. This would be the removing order, or the losing order, or the oxidation order. And so this would be the oxidizing, like I called it 3 different things. I called it losing, oxidizing, removing order. It's different. And then you start here. You start from the bottom and work up. Start bottom and go up. Filling order, you start from the top and go down. Okay for that? So what noble gas is it isoelectronic? Iso just means the same electron. So what noble gas has this electron configuration? Argon. This would be argon. With 18 electrons. All right, so that's the answer to the active exercise there. Let's move on here. So ionic compounds, you know, why do we form these ions? We form these ions to form ionic compounds, and when we form bonds, bonds release energy. When you make bonds, it's exothermic. Because if you have to break bonds, let's say I need to break the bonds in this ruler, or this yardstick, or meter stick. In order to break bonds, does it cost energy or does it release energy? To break, it costs energy. To form, it releases energy. So when we form bonds, things become more stable. And so why do we want to form ionic compounds? Well, we want to form ionic compounds because we're going to form bonds, which means we're going lower in energy, becoming more stable. That's what we want. So ions are held together by ionic bonds, and ionic bonds are just electrostatic attraction, Coulombic type attraction, the attraction between positive and negative. That's it. And these are like balls. Nearly all ionic compounds are solid. In fact, all the ionic compounds that we deal with are solids at room temperature. You can melt them, you know. I've tried to melt. Have you ever tried melting table salt?
No.
It's hard to melt. I've tried melting it, but I couldn't melt it. Yeah. That's because it melts at 700 plus. So I think it's like 770 degrees C, which would be what in Fahrenheit, you know, well over 1,000 Fahrenheit, that's why I couldn't melt it. Anyway, nearly all ionic compounds are solid at normal temperatures and pressures. The solid has a definite geometry called the crystal lattice. You know, the shape of this depends on the shape of the ions, you know, and the size difference. When you get different, you know, arrangements of stuff. Like, for example, a carbonate ion has a weird shape to it, and so it forms a different kind of crystal structure. And we see that crystals come in all shapes, right? They come in lots of different shapes. Ionic compounds, you know, they're always neutral. We have to have the same positive net charge as the net negative charge. You know, they've got to be electrically neutral. Otherwise, we call them an ion. We don't call it a compound. The bonds in an ionic crystal are very strong, which is why most of them are solids. You know, strong bonds means it's hard to break, hard to melt, that kind of thing. if you melt them, they're pretty good conductors of electricity. As solids, they aren't. You know, like solid sodium chloride is not a very good conductor of electricity, but molten sodium chloride is a good conductor of electricity because the ions can conduct electricity. In the solid state, there's no translational motion. So that's right. Although right before it melts, sodium chloride does something interesting. A lot of defects, you know, get introduced into the crystal lattice, making solid sodium chloride right below the melting point a good conductor of electricity. This is a reaction between sodium and chlorine. Sodium is a powerful reducer, chlorine is a powerful oxidizer, so it's going to result in a violent reaction here. Explosive. We can see this. We can see this. The yellow color comes from sodium atoms being excited. This yellow color you might see in old street lamps. Have you seen yellow street lamps? The yellow street lamps have sodium metal in there, and they heat it up and vaporize it. And then they excite the electrons in there, and it starts to emit yellow light. That would be a sodium lamp. We call it a sodium lamp. Like I said, anything with electrons, you should be able to excite the electrons and make light. But you know, sodium light is not white light. It's not when something emits white light, we call it continuous or discontinuous line. Yeah, white light's continuous. The sodium is not emitting white light, it's emitting line spectrum. Actually, let's take a look at the reaction of two things. Let's look at the reaction between sodium and chlorine. So the reaction between sodium and chlorine, there, let's see a video, short video on that. Sodium, chlorine. Making table salt. We'll do this one. This is only 51 seconds. This chlorine gas, it's a yellow gas.
A piece of sodium metal is placed in a flask containing yellow chlorine gas.
So that's a tiny piece of, usually when you do reactions, you start off small, and then you slowly add. You know, you just don't dump in a large quantity because that can generate explosions, so we always be careful.
The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
You see that cloud is just white sodium chloride, table salt, basically. Whether you need to initiate the reaction with something or not.
Table salt is also known as sodium chloride. So just from the name sodium chloride, you can pretty easily see that it has two major components, sodium and chlorine. On their own, both elements, sodium and chlorine, are pretty reactive and dangerous.
It's interesting, they have sodium street lamps there.
When they're combined, they form a nice edible salt. This is an interesting demonstration that shows how drastically different the properties of the compound can be compared to its components. So for the first step, I'll cut off a small piece of sodium that I'm going to be using for the reaction.
That's wet with mineral oil there.
Sodium metal is actually quite shiny, but it quickly reacts with air and moisture and forms a white coating. You can see a bit of the shininess after it's cut on the bigger piece. The liquid that you see dripping off the sodium is mineral oil, which is what the sodium is stored in. This is my chlorine generator. Inside the flask is chlorine pool pellets. I then poured hydrochloric acid into the flask and it reacts to produce chlorine gas. As you can see, the chlorine has a faint greenish yellow color. The top is blocked, so the chlorine is forced down the hose. The hose leads into a larger flask with sand at the bottom. Inside the flask is then dropped a small pellet of sodium. This is half of the piece that I cut off in the earlier shot. A little water was added to get the reaction started, but I think I added a bit too much.
You're going to have water react with it too.
Suspension of really small particles of sodium chloride. The white stuff on the walls is also sodium chloride. When a lot of the sodium chloride cloud has dissipated,
That's
it's
not a very
easy to
clean
see
reaction.
A lot of the white sodium chloride all around the flask.
Alright, so
decided to
that's the
try it
reaction
again, but this
there.
time put it.
Sure. Well, that's okay. That's enough. For that. This is a sodium vapor lamp, and so we just put some sodium, metallic sodium in there, vaporize it, and then excite the electrons. When they excite the electrons, then we can see the line spectrum from that. So let's take a look at the line spectrum. You know, yesterday I was asking about the history. The history started off with spectroscopy. What was spectroscopy again? Measurement of light. Yeah, interacting with matter. That's good. Sodium has a very interesting light spectrum. You definitely aren't getting all the colors of the rainbow. We're looking, this one's going Roy G. Biv this way. A lot of them go Roy G. Biv the reverse way. It doesn't matter, you know, it's like right side up, upside down. It doesn't matter because we just remember red and violet, so it's easy to see where we're at because violet's over here, red is over here. And so in our book, they put red over here and violet over here, but it doesn't matter. But if you take a look at the sodium lamp, there's only one. Actually, if you have a higher precision instrument, you'll see two lines here, two sharp lines. That's it. That corresponds to an electron in a 3p or something, or I forgot the transition. But it was a transition that's associated with that. Now, this transition is quantum mechanical. So quantum mechanics can't explain or describe this transition. So let's take a look at the yellow transition, electronic transition. There's sodium. This is the quantum mechanics. This chart looks a little, you know, this energy level diagram looks different than the one you've memorized, right? Or the one you're starting to memorize, or the one you're going to have memorized, correct, for the next test. This looks different because this one has additional things built into it. The additional things are that we have to keep track of, or angular momentum and this kind of stuff. We're just looking at transitions here. The yellow lines are a result of an electron in 3p. So in normal sodium, 3p's are empty. So an electron can get excited to a 3p orbital. Electron gets excited to 3p, and eventually it doesn't stay back there forever. It drops back down to the 3s, where it's normally resides. And that's going to emit the yellow light. However, if you excite it to higher levels, you could emit infrared, or you can emit ultraviolet. So there are a lot of lines in infrared and ultraviolet, but only two lines are visible. They so happen to have just about the same energy. This one's a 589.0, this one's a 589.6, just slight difference in energy depending on the spin of the electron. That's what do we call this? We call this the energy or orbital energy level diagram. We call this what do we call this thing on the top? The spectrum. If we make a lamp out of mercury, it's going to look funky as well. Lithium's going to look weird. Hydrogen's going to look weird. None of those are going to make good reading lamps. But the sodium street lamps, you know, they're cheap. They're pretty efficient at using. electricity, they generate a pretty intense yellow light, so useful. So it's kind of interesting. He had a sodium street lamp in the street of his house. So where does all that energy come from? Why is so much energy being released there? Well, the electrons are unstable. Why are the electrons unstable? The light's being emitted. This yellow light's being emitted because the sodium atoms in there before they react and start emitting yellow light like the street lamps. So electrons get excited, but what's exciting the electrons? This is a very energetic reaction because a lot of energy is being released. It's exothermic. Why? We're making bonds. We're making the lattice, making the crystal lattice. How hard is it to melt sodium chloride? Very hard. That tells you the lattice is very strong. That tells you the bonds are very strong. We're releasing a lot of energy here because we're making this crystal lattice, which is very stable. So it's a violent reaction. And so that's why we make the ions. You know, you make the ions here. This is sodium. Take a look what happens to the size. It's very interesting what happens to the size. Chlorine is smaller than sodium. Chlorine's smaller than sodium because when we look at the periodic table, obviously you probably should look at the previous PowerPoint that I had earlier. Chapter 11. We know that sodium is bigger than chlorine, right? The size goes down. Why does the size go down again? Or does it go left to right?
Because they're closer to one place.
More protons is the answer. More protons is going to have that, in science fiction, it would be they have the tractor beam effect on the electrons, pull the electrons in closer, more protons. Or just, stronger electrical. But, potassium has more protons than sodium, but potassium is bigger. Why? That's not the reason. It's not because of more neutrons. It's because of more. Not there, because the more electrons here. Chlorine has how many electrons? 17 electrons. Sodium has 11 electrons. So chlorine has more electrons, but it's smaller. And so you have to give me another reason why.
It has
This is critical for studying. It's already like the halfway. Yeah. Okay. That gets to the reason. There. Yeah. More orbitals. And so you got to think about this class. Let's say you want to do better in this class, and make sure you don't let stuff slide. Like we were talking about this size thing yesterday. If it doesn't make sense, make sure to get cleared up. Today at the beginning of class, ask me about it, and we'll go over it again. But don't wait until otherwise these type of things fade. But yeah, it has more orbitals. Well, it has more orbitals going left to right too. You got to be more specific. It has more shells than the outermost orbitals are big ones. This one has more shells. So we build up. That's the reason. The thing is, the repetition thing is important. If you only just see it once and leave it there, you aren't getting the repetition. So this chart, if you want to know the chart, you just go over it again. We talked about this chart yesterday. Hydrogen to helium. Helium has more protons. It gets smaller, right? And then we add a shell. The size gets bigger. And now we're in the same shell. We add more protons. It gets smaller, as we'd expect. Then we add another shell. It gets bigger. And then we go up, you know, and we're in the same shell, we add more protons, it gets smaller. This kind of repetition helps. Initially, it might not make any sense, but you just memorize. And when you memorize it, then eventually things will click and make sense. But some people, you know, some people want they want it to make sense. But things, you know, as things get harder and harder, they don't make, if it were easy, then, you know, you could teach it to anybody. You know, in kindergarten, you know, but the stuff gets harder and harder, and it takes more time to digest, and that more time means, you know, the repetition part comes in. And so if you want to do better, make sure you go back through this stuff. But anyway, we know that sodium is bigger than chlorine, but a weird thing happens with the ions. Take a look at what happens. The size gets flipped. The reason the size gets flipped is when sodium loses an electron, now it has 11 protons and 10 electrons, so that attractor beam, the Coulombic attraction, is stronger. So the size shrinks. But now the opposite effect happens with chlorine. Chlorine is 17 protons, but now it's got to take care of 18 electrons. And so if there are fewer protons taking care of more electrons, then the electrons are going to scatter more. So it's going to grow bigger. The rule of thumb here is this. The rule of thumb is when we form a cation, the size gets cut in half. And so sodium ion is about half the size of the sodium atom. The opposite happens with anions. When you form an anion, the size typically doubles. And so chlorine going to chloride doubles in size, sodium going to sodium ion, it's cut in half. And so this is why I wrote the chloride ions earlier as being bigger than the sodium, whereas it should have been the opposite. You know. Here you can see, without them even telling you what the green and the gray are, I automatically know what the greens are. The greens are chloride, because they're bigger. The grays are sodium. They're smaller, so it's easy for me to see that right off. So this is, what is this called again? Ionic lattice. I just talked about the nearest neighbor, but the ionic lattice has a lattice of bonds. A lattice of bonds is very tricky because of this. The nearest neighbor to a sodium are green chlorides, but the next nearest neighbor, that is, okay, this is the nearest, and the next nearest would be sodium. That's a repulsion, because positive hates positive. But the next nearest would be chloride, which would be an attraction. And so a lattice is this. A lattice doesn't consist of one bond. It doesn't consist of 6 bonds. It consists of a lattice of bonds. A lattice of bonds is where you sum up all the attractions over 3 dimensions and all the repulsions over 3 dimensions, and you come out with a net attraction. And so this is a lattice. That's what makes salt pretty strong. Although salts, you know, these are easy, they're brittle, they're easy to cleave. And that is, it doesn't take much force to offset this. If I just push this chloride a little bit to the right, then who's the nearest neighbor? If I push this chloride a little bit to the right, who's the nearest neighbor? Another chloride. Chloride and chloride, do they attract each other? They repel. So what happens is the whole layer breaks off. That's called cleavage. So if you take a razor blade, this is really easy to cleave because you just push or offset the ions, and then you get net repulsion as the nearest neighbor. But it's really hard to melt this stuff. This is called the rock salt lattice. These lines are just to show the geometry. These lines don't represent a bond. These lines would represent a covalent bond, but these are not covalent bonds. What holds the ions together is being next to each other, charged ball. And so this is just to spread it out. You know, you take this. Have you ever seen those drawings where they expand?
Yes.
So you can see the details. That's what they're doing here. They're just separating. So it's like an accordion. They separate it out so you can better see how everything's attached. And they can collapse it back in. So this is what we normally see. This is normally how crystal lattices are generated, so we can easily count. For example, this how many nearest neighbors does it have. So these links show the nearest neighbors. Here we can see 6 sodium ions surround each chloride and vice versa. That's what we call the nearest neighbor. Those are 6 ionic bonds holding it there. Solid sodium chloride doesn't conduct electricity very well, but molten sodium chloride does, because in molten sodium chloride we have translational. This is molten sodium chloride here. Actually, this might not be sodium chloride. This could be some other low melting salt. This looks like another low melting salt because it's hard to melt. There's other salts that don't have as strong of lattices that are a lot easier to melt, like cryolite. There's ionic bonds and ionic lattices, but not everything is going to form an ionic bond. You know, some things form another type of bond, which is called a covalent bond. So if we have sodium has relatively low ionization energy, and then chlorine. And then the chlorine's going to have no problem stripping that electron with sodium. Chlorine wants that electron, can take it. What results? What results is sodium chloride. This is called the Lewis structure. Sodium chloride. Lewis structure. How about if I do chlorine versus chlorine? So I'll put one chlorine here and another chlorine here. Chlorine versus chlorine, which chlorine would win? Yeah, actually in this situation, they're both equal in strength. And they're both going to try to take the electron, but are they going to be successful? This chlorine is going to try to take this electron, this chlorine is going to try to take this electron, but will either be successful in removing the electron? No. What's going to happen is they're going to result in a tie. And this tie is that they're both pulling on the electron, and neither is going to win. But it is not a no-win situation. It's a win-win situation. It's a win-win situation because if they do this, then what we do is we look at the number of electrons surrounding the chlorine. The number of electrons surrounding this chlorine is what we call an octet of electrons, 8 electrons here. The number of electrons surrounding this chlorine is an octet. And so even though these two are going to be shared, we end up with a net effect here that chlorine's filled its octet, its outer shell. And so this will be shared pair. That shared pair we show differently. This is one way of showing it, which is fine. We could show it like this, or we could show it like this, with a line. Each line represents a shared pair of electrons. So this would be what we call a single bond or bond with you know, here we actually show the bond here. This is the bond. Here we don't show a bond. It's just the ions adjacent to each other. So this is a covalent bond. Covalent bond. So it turns out it's electrical attraction that holds these two chlorines together, but you're thinking, well, each chlorine is neutral. How do we have electrical attraction? It's electrical attraction between the protons in the nucleus and the shared bond that's holding the shared electrons. It's holding it together. And so that's covalent bond. This is a Lewis structure also. These are Lewis structures here. Note the Lewis structures are quite different. Ionic compounds have a very different Lewis structure than covalent compounds. This is ionic. Covalent compounds are molecular in general, most of them are, but some are covalent lattice compounds. here they're just talking about molecular, but not all needs to be molecular. So, for example, diamond is held together by covalent bonds, but it's not molecular. Chemical bond between two or more atoms that share a pair. Bond is permanent until broken by chemical change. Okay, it's hard to break that bond. It costs a lot of energy to break that bond. Molecules, you got that, but not everything forms molecules. Some things form atoms. So H versus H. H can either lose an electron, get a +1, or it can gain an electron to go -1. If it gains an electron, it'd be isoelectronic with helium.
So covalent bond is easier to break than lattice.
Ionic bonds?
Oh no, covalent.
No, covalent bonds are hard to break. Ionic bonds are hard to break. Both of them are hard to break.
So it will be compared.
If you were to compare them, you have to. It's hard to compare them. But in general, ionic bonds, it's hard to compare them because if you think about diamond, what's the melting point of diamond? Is it higher than salt or lower than salt? It's higher than salt, right? But if you think about some other ones, they're a lot lower, and so it's hard to compare. Both are very strong. To compare them, you need more information. So you can't just say. But if you look at the pattern, lattices are typically on the order of what we call a double or triple bond in strength. The double or triple bond is when you have multiple bonds occurring there. So far, we're only looking at one single bond. This is the formation of H2 here. Let's look at some other. I don't know why this is in here, but pure water, the bonds are hard to break in pure water. Pure water is H2O. H2O are neutral, so it doesn't conduct electricity between these two. These are called electrodes or leads. Sugar consists of neutral molecules. They don't ionize or dissociate in water. Stay together. Sucrose. Salt, one way, even though salt has strong bonds, the waters can pluck apart these ions. This conducts electricity. Table salt. Okay, what holds the covalent bond together? What holds the covalent bond together is electron cloud or charge density formed between the two electrons is concentrated in the region between the two nuclei. So, what we see here for chlorine is this. For chlorine, what happens is the bonding region here, the electron cloud is concentrated here. So this is negative charge density. So that's a negative electron cloud. However, in the nucleus, we have positive charge in the nucleus. I'll just write these down. Positive charge in the nucleus. And so the electrical attractions between this negative charge here and the positive charge in the nucleus. Here's a negative charge out here, but this is the bond. How do we get this negative electron cloud here? Well, that just so happens that this chlorine is going to have a 3p orbital. If you recall, the 3p orbitals look like this. What do the s orbitals look like? They're like a spherical. And so what we have here is we have one electron in this 3p orbital like this. And then we have another electron in the 3p orbital like this. These are two 3p orbitals. The other electron belongs to the chlorine. And so this is called 4p orbital overlap. Orbital overlap like this is going to increase the probability density here. So the cloud in the overlapping region is going to be more dense than the cloud outside the overlapping region. So we have a higher probability of finding the electron in the overlapping region. And so this is orbital overlap. Orbital overlap. So covalent bonds are formed by orbital overlap. Orbital overlap, merging of two atomic orbitals and their associated electrons to create a covalent bond. Half-filled orbital, what they're talking about here is one electron comes from this. You know, to fill this orbital, we need two electrons, right? And so one electron, that's called a half-filled. There are other orbitals on this that are filled. So there's another p orbital, which is perpendicular to this, that has two electrons. And another p orbital that is perpendicular that has two electrons. So I'm not going to show them because it's going to get too messy, the drawing. This is the orbital overlap. Hydrogen has one s orbital, so it's easier to see with one s orbital. The 1s orbital looks like this. This is the cloud. What I'm showing is the boundary, you know, the 95% boundary. And so we take this 1s orbital and overlap it with this 1s orbital. And what we're going to see is the density of dots is going to increase between them. And on the outsides here, there's no overlap. So in the overlapping region, we're going to have a higher density of dots. The higher density of dots means the protons are going to be more attracted to this region here and hold the two atoms together. So this is the covalent bond here, H2. H2. Here's fluorines. So this is the way we can show fluorines like I did with chlorine. You know, this fluorine's going to try to strip one, this fluorine's going to try to strip one. Eventually it's just going to result in a tie, like that. They say or this. I don't like this one here because this one doesn't show all the valence electrons. In the Lewis structure, we should show all the valence electrons. And so do not write Lewis structures like this. You're only allowed to write Lewis structures like that when you get to organic chemistry, because at organic chemistry they expect you to be able to visualize all the electrons here without drawing them. Can you tell me what it looks like? No, probably not. So you can't do that. You got to draw out the whole thing. If you looked earlier, I didn't draw the lone pairs there. These are called lone pairs. I didn't draw these pairs of electrons earlier because I talked about them. But from now on, I'm always going to draw the lone pair. Lone pair is a pair of valence electrons in the molecule that are not used for bonding. A bonding pair is this. And so over here I have one bonding pair, 3 lone pairs on this chlorine, and over here I have one bonding pair, 3 lone pairs. But this bonding pair is used for both. So we double count. You know, this is why I double counted the bonding pair. The lone pairs I do not double count. Those lone pairs belong only to this chlorine. But this bonding pair is shared between both, so I'll count them 2 times. One for this, one for this. And so both of those end up with 8 electrons, but I don't have 16 electrons total. We use the octet rule. We want 8 electrons. The octet. Not everything needs an octet though. For example, hydrogen doesn't want an octet. It'd be crazy to put 8 electrons around hydrogen because hydrogen is only in the first shell. How many electrons does it take to fill up the first shell?
2.
Only 2. So hydrogen has a duet, not an octet. Duet. Okay, it depends on this tug-of-war. What I showed you was too extreme here, as far as the tug-of-war goes. sodium easy to oxidize? Yeah, sodium's easy to oxidize. Is the ionization energy of sodium high or low?
Low.
Very low. Very low, easy to oxidize. Chlorine comes along, has no problem. Flex that electron off. Good. Now chlorine has knocked head. Sodium's okay. Okay, then we're going to go to hydrogen, and then we're going to go to chlorine. Is hydrogen easy to oxidize? It's a lot harder to oxidize hydrogen than, hydrogen's still not bad. You know? But the ionization of energy of hydrogen is a lot higher, so what tends to happen is this. Chlorine comes along, and it's going to have a harder time pulling that electron off. In fact, hydrogen does not completely let go of the electron. And so what results here is this. If I look at the cloud here, that cloud of electrons belongs to chlorine alone. I'm not going to look at the other electrons. But in this case, hydrogen doesn't completely lose. And so what happens is this. Chlorine is stronger, of course. Chlorine's stronger, so it's going to pull most of the cloud to it, but chlorine doesn't completely let go. And so the cloud looks like this. Here the cloud is entirely on chlorine. Here the cloud is what we call, is that symmetric or asymmetric? This is asymmetric. Showing what we call polarized. You know, what happens is chlorine really wants this -1, but hydrogen isn't going to give it up. And so what we're going to end up with is something called delta minus and delta plus. Do you know what delta means? Yeah, it means a small change. And so in the context of this, it means a negative charge between 0 and -1. More like -8 or something like that. And so it doesn't quite end up with the whole cloud. It wants the whole cloud, but it doesn't. But hydrogen is weaker, and so it's going to get more of the cloud. And so more of the cloud gets there, more negative charge gets there, but not all of it. This is what we call polar covalent. Polar covalent. This is what we call ionic. And then chlorine, DS chlorine is going to make a non-polar covalent because the cloud is going to be very symmetric. Now, now for the Lewis structures, we just show them differently. The Lewis structure for sodium chloride can look like this. The Lewis structure for HCl looks like this. We don't show anything different. You know, the bond's going to look exactly the same for chlorine as it does for HCl, but we have to recognize that they're not exactly the same. This one is going to be polar covalent. This one's going to be non-polar covalent. Both of them are just going to be a single line. Now, how do we know which one, how do we know the tug of war? This is a tug of war. How do we know their strength? How we know their strengths is via what we call their oxidizing ability, ionization, reducing ability. So here's where it's a tie. Here's where winner takes all, basically. Here's somewhere in between, depending on the strength of the left atom. How we know that strength of the left atom is basically this. Electronegativity. Electronegativity is going to tell us the strength in the tug of war for electrons. So if we're looking at rankings, tug of war rankings, its electronegativity would be the tug of war ranking. Do you know who would be the strongest? Atom, strongest element, atom. Fluorine. Fluorine is going to be the strongest in electronegativity. And we give it a ranking. The ranking scale goes from 0 to 4. So we're on. We'll go on a break. We'll go on a break now, and then we'll start with electronegativity after break.